That brings us to the next section, errors and error measures. Yeah, so there are some nice overviews. Well, obviously a quite seminal paper by Hindman and Köhler that also proposed a MAE, an error measure that we see later, and then a paper of my PhD student and another collaborator and myself, Heva Malage et al. 2023, which covers pretty much everything I'm talking about today in a quite extensive way. So it's quite long paper talking about all of these things. Yeah, maybe a bit surprising is that how to calculate errors, error measures in forecasting. It's still controversial. No solution is out there that always works. So there are still papers proposed, papers published in the literature that come up with their own ad hoc measures or that just propose a new measure. So yeah, it's still kind of an active research area, and measures are also often misused, right? And it's kind of surprisingly complicated. So yeah, that's what we are going to go into quite deep in the following. Okay, but let's start with the basics, right? So an error usually has two components, which is bias and variance. So just to illustrate that with this kind of, arrows where you want to hit a target. So what you ideally want is a method that is kind of like this, right? So that hits the target quite well every single time. This method has low bias and low variance. Now, if you still kind of hit correctly around the target, but you just have a very wide spread, right? Your method is unbiased. So you still kind of know where hit the target correctly. You're just not very accurate at doing it. So this method would have low bias and high variance. Now you could have, well, maybe you have a method that is quite reliable. It always hits the same spot, but it's just the wrong spot, right? So this would be a high bias, low variance method. And now you can obviously also have high bias and high variance. That would be you're just hitting the wrong spot and you're also not hitting it very reliably. Okay, good. So how do we measure bias and variance? So bias and variance have different consequences for business. Yeah, so it's good to look at them separately, because think about it. If we always underpredict, that may lead to always having stockouts, right? So maybe our forecast is not so bad in terms of accuracy, but it's just biased. It's always too low. So yeah, could have certain consequences. How would we measure bias? So, well, we can measure bias just by the mean error, right? So it's not the mean absolute error, the mean error. So we don't take absolute values here. We just take the error, which is the actual YT minus the forecast of YT, which is here YT hat. And now we just take the mean over the error. That's the mean error. Okay, now the mean error can obviously be positive and negative. If it's positive, greater 0, that means the model underpredicts on average. It is negatively biased. If this mean error is smaller than 0, it overpredicts. It is positively biased. So the bias is minus the mean error. I mean, I could have also just switched around here forecasts and actuals in this difference, and then it would be directly the bias. But anyway, we're using this definition. So yeah, we can calculate the bias through the mean error. Okay, now how can we measure variance? Well, I mean, maybe if you remember some introductory statistics class that you heard at some point, that we could calculate the sample variance by taking just the mean over the series. And by the way, I think here this should not have a t, so it's basically just Sure. Like, okay. So it is the yt minus the yt hat, and then over all of them, we take the mean so that we get the mean, and then we subtract this overall mean from our current error, square it, and now we need to take here n minus 1 because it's a sample variance. Yeah, okay. And now if we assume that the true population mean is 0, which means our method doesn't have bias, then we can actually use this different formula. So this mean here is 0, it goes away, and then we have 1 degree of freedom less because the mean is now known, it's 0. So that's why we go back to dividing by n and not by n minus 1. Yeah, and with that we get this error standard deviation. Yeah, okay. And now with that we can start calculating, well, some scale-dependent errors, right? So we can get a squared error, which is this one here, yt minus yt hat squared, and we could do absolute errors, where we just do absolute errors. And now we get the corresponding error measures, like a root mean square error would be just the square root of the mean of that error, and the mean absolute error would be the mean of the absolute error. And now you have probably noticed that this RMSE formula is actually exactly the same as this one here, which was this error standard deviation, right? So the MSE is equal to bias squared plus variance. So if our model is unbiased, if the bias is 0, then RMSE measures exactly the standard deviation of the error. Yeah. RMSE and MSE are minimized by predicting the mean of the forecast distribution. It penalizes large errors more heavily because it squares. And minimizing RMSE leads to a mean unbiased forecast. Okay. Now, MAE, the mean absolute error, this is sometimes also called mean absolute deviation. So if you see somewhere written MAD, that's the same as MAE. It is actually minimized by predicting the median of the forecast distribution. It's more robust to outliers and large errors therewith. But obviously minimizing MAE can then lead to mean biased forecasts if the forecast distribution is skewed and the mean and the median are not the same. Another thing that is important for series with small integer values, minimizing MAE will lead to predictions that are small integers because the median of the forecast distribution is an integer. And what that means in particular is that for intermittent series, minimizing MAE can lead to predicting only zeros and heavily biased forecasts towards underprediction, as the median of the forecast distribution is a 0, right? So if your data has more than 50% 0, the median will be a 0. So using MAE as your L1 loss as your loss function, you will predict only zeros. Yeah. So MAE and L1 loss are not good if you have intermittent series. Okay, so yeah, these are the scale-dependent measures, RMSE and MAE. So their advantages are that they are on the same scale as the data, so they are quite interpretable. So you can say, well, I have these products, I have product sales. So MAE gives you some sort of average amount of sales that you're going to be off. But the problem is that if the series are on very different scales, then some series will dominate the evaluation, right? If you have some products that you sell in the tens of thousands and some products and many products that you sell only 3 to 4 every day, then obviously this one or this few series that have very high values will dominate RMSE and MAE. So if you want a measure that kind of is scale-free, so that every series is kind of treated equally in a way and not some series dominate, we want to have a scale-free measure. What that means is we need to divide by something. We need to normalize this measure. And now it turns out that it's incredibly hard, right? So after 30 years of research in forecasting, we have still not found this something by which we need to divide in a way that it works under any possible non-stationarity and any series characteristics. There are over 40 error measures proposed in the literature that I know, and we are going to look at some of them now in the following. Yeah, and problems are that series can be very, very different, right? If you say, I want something that works for any time series, okay, so it needs to work for non-stationarities like in this air passenger series, which is a multiplicative seasonality and multiplicative trend. You could have something like a random walk with stochastic trends. You could have a very seasonal series with no trends, and then you can have these intermittent series with very low values. And now it's just very difficult to find something that works for all of these different characteristics.